Okay, so we're going to be talking about voltaic cells. So in this chapter, you see many examples of the roles that metal play in the lives of humankind. You have also seen how different rates of chemical reactions make some metals more susceptible to the effects of corrosion than others. For example, silver jewelry can tarnish, whereas gold jewelry does not. While corrosion is usually seen as an unwanted effect, it is sometimes helpful. So copper artifacts that were made thousands of years ago by ancient ancestors of the First Nations people in Canada, for example, were preserved by a protective surface layer of green corrosion, basic copper carbonate. In each of these cases, oxidization and reduction play a key role in describing the reaction. In this lesson, the focus shifts from the corrosion of a metal surface to the applications that make use of the flow of electrons between different metals. So um, you know from some of your own experiments that many modern devices operate using voltaic cells. What most people call one of these devices is a battery. However, a battery usually refers to a group of cells that are connected together. A battery of voltaic cells in a graphing calculator provides a continuous flow of or current of electrons when the calculator is operating. The different components within the calculator convert the energy from the current into other work. This transfer of energy allows each component to accomplish its designated task. As one set of electrons leaves the battery of voltaic cells, the other group enters to keep the device working. A graphing calculator operates because the components can access the energy within the current of electrons that continuously loops through the circuits. So, what causes the river of electrons to flow in the first place, and why do electrons leave one end of a voltaic cell and return to the other end? Answers to these questions involve reduction and oxidization reactions, combining metals that have a tendency to lose electrons with metal ions that have a tendency to gain electrons. So a voltaic cell is a device that spontaneously produces electricity by redox reactions, and a battery is a set of voltaic cells joined to produce an electric current. So inside a voltaic cell uses the transfer of electrons between chemical components to create an electric circuit that can flow through an external circuit. The connection of this external circuit is made through wires that contact each electrode of the voltaic cell. As one substance in the cell is oxidized or loses electrons, another substance in the cell is reduced or gains electrons. In the next investigation, we'll have the opportunity to explore the oxidization and reduction reactions that occur inside a voltaic cell. So an electrode is a solid electrical conductor in a cell that connects the cell to an external circuit. So, how voltaic cells work. Early in this chapter, we investigated the activity series for metals and metal ions. This series describes oxidization reactions where metal atoms lose electrons and become metal ions. The chart also describes reduction reactions where metal ions gain electrons to become metal atoms. Placing a metal that readily loses electrons into a solution that contains metal ions can readily gain electrons results in a spontaneous reduction oxidization or redox reaction. The voltaic cell featured in our Building a Voltaic Cell investigation used these principles to transform chemical energy into electrical energy measured by the voltmeter. The following analysis shows how a voltaic cell can produce a steady electric current to an external circuit. So step 1, we need to identify the electrode where the oxidization occurs and label it. So an anode is an electrode where in a cell where the oxidization half of the reaction occurs, and the cathode is the electrode in the cell where the reduction half of the reaction occurs. So locate each metal used as electrodes in the activity series. These metal atoms are located on the right side of the series. Recall that the metal atoms located closest to the bottom of the chart have the greatest tendency to be oxidized or lose electrons. In this case, zinc is located below copper. So the zinc electrode is the one that loses electrons or is iodized. And this electrode is called the anode. The copper electrode is the one that will be receiving the electrons or is reduced, and this electrode is called the cathode. So here is a memory device to help you remember labeling your electrodes. So anode and oxidization both begin with vowels, where cathode and reduction both begin with consonants. So describe the oxidization process at the anode. So write the half reaction that describes the oxidization process at the anode. So in this case, it is zinc solid goes to zinc aqueous plus 2 electrons. The zinc strip will decrease in mass and become smaller over time because the zinc atoms are turning into zinc ions. Electrons lost by the zinc electrodes travel to the external circuit. From the point of view of the voltmeter, the zinc electrode is a negative electrode because it is the source of the electrons. Here is a memory device to help you remember the charge of the anode as seen by the electrical circuit. So A no is negative. So again, there is read as anode is negative. And here's a memory device to help you remember which way the electrons flow in the external circuit. So electrons flow from A to C, so the anode to cathode. So describe the reduction process at the cathode. So the copper 2 ions in the surrounding solution are attracted to the electrons, thus gaining electrons to become reduced copper atoms. Copper 2 ions precipitate on the copper metal strip, causing the mass of the copper to increase. As the cell operates, the intensity of the blue color of the copper 2 ion solution in the beaker decreases as the copper 2 ions are being reduced. Electrons are conducted from the external circuit to the copper cathode. From the point of view of the voltmeter, the cathode is positive electrode because it is attracting the electrons. So a memory device to remember this is a cathode is positive, or read as a cat's paws. Okay? So describe how the cell bridge completes the circuit. So the previous steps describe the flow of negative charge in the form of electrons from the zinc anode to the copper cathode. In this situation, it is not sustainable because the electrons cannot be produced at the anode without a limit. The charges must be replenished. A salt bridge provides a path for ions to complete the circuit. The salt bridge allows the SO42 negative ions or anions to move to the solution containing the zinc anode. And the negative ions are attracted to the excess positive zinc ions accumulating in the solution. The sodium ions will migrate to the cathode side, where the solution has lost its positive ions as the copper 2 plus aqueous ions are reduced. This closes the loop and completes the circuit. The absence of the salt bridge to balance the charge on both sides of the voltaic cell inhibits the reduction and oxidization reactions, thus not allowing the voltaic cell to function. So a detailed diagram showing a voltaic cell is useful for explaining all of the components of a cell's operation. However, sometimes it is useful to communicate the essential features of a voltaic cell as a more abbreviated format. This is concisely illustrated as follows. So in this format, it is called cell notation. And in this arrangement, one electrode is always put on the left side and the other electrode is always put on the right side. The vertical line represents the boundary between the metal and its ion in solution, and the double line represents the salt bridge. So cell notation is a concise description of a voltaic cell. Voltaic cells for consumer use. So although the setup with the two beakers and the salt bridge is ideal for learning about the operation of voltaic cells, this apparatus is not suitable for everyday use. Most people use voltaic cells are conveniently packaged in a small sealed container like that of a consumer cell, shown in this figure. So even though the cells are called dry cells, they actually contain a moist paste as an electrode. If these cells were completely dry, they would not work. The small cells consumers use to operate on the same principles of oxidization and reduction that we've been applying throughout this lesson. The oxidization reaction is straightforward and can be found in the activity series for metals and metal ions. The reduction reaction is more complex, requiring a number of interconnected steps. In North America, about 3 billion consumer cells are purchased every year. The metals and electrolytes that enable these cells to produce an electric current are harmful if released to the environment. So you can help these substances keep them out of landfills by sending spent cells to a local recycling center. Another strategy is to use rechargeable cells, which dramatically reduce the number of cells needed over a product's lifetime. And that is everything. Thank you very much for watching, and we'll see you next day in class.